Assalamu alaikum everyone. So lecture number 20, and today we will be talking about signal encoding techniques, and we will be having review questions. And what we will be doing, we will be discussing those topics that are relevant to the review questions, and we will quickly go through those topics, and this way we will be having recap of the underlying chapter. And these are the bullets which are topics which we will be talking about: differential encoding, then the functionality performed by modems, and the advantages that is provided by the digital over analog. Then we will be talking about ASK, amplitude shift keying, and there are certain limitations when we have to represent binary digits, bits, by using ASK. And then after that we will be talking about one of the digital encoding, that is NRZ, and we will be talking about the pros and cons of that encoding scheme. And then we have to compare quadrature phase shift keying versus offset quadrature phase shift keying, and finally we will be talking about quadrature amplitude modulation. So let's start. So we have to define differential encoding over here, so we will be having a recap of the encoding. So when we talk about the signaling techniques, so our objective is to represent data in a suitable way, in an efficient way, and then ultimately we have to launch that data over to some medium. So there is an issue of performance and efficiency and the compatibility, right? So we want to represent data in an efficient, effective way, and we want to avoid errors. We want to use the minimum amount of bandwidth in order to transmit maximum data. So these are some of the issues. So of course we are also conscious about the cost and complexity of the underlying communication system. So the objective is to represent the data by using some signaling technique, and that data has to be launched, or those signals has to be launched over some medium in order to have transmission from one point to another point, right? So there can be different use cases. We can have digital data, for example data from the computer. So the medium which is going to be used in order to launch or transfer data can be digital, and the examples and the schemes which we have, or the choices which we have, they are NRZ-Manchester, Differential Manchester. So these are the signaling techniques which we can use. Then we can have analog data, for example our voice, and the medium can be digital. So it's again we have one choice over here, and then we have another scenario where we have digital data and we have to use analog medium. So in that case we can use modem, so it will be modulating and demodulating. So when sending the data over to the analog medium, so it has to modulate, and then when it is receiving data, and it has to convert that data into those signals into digital data. So in that case it will be performing demodulation. So there are some modulation schemes: amplitude shift keying, phase shift keying, and frequency shift keying. And then we have another use case that the data is analog and the medium is also analog, right? And in that case we have certain choices in order to use some signaling technique: AM, amplitude modulation; FM, frequency modulation; and the examples are conventional radios and television data transmission. So when we talk about the signaling techniques, they deal with that how we are going to transport bits over some physical medium. There are certain issues that we have to take into account. First of all, timing of the bit, when it's going to start and when it will be going to end, and the duration of that bit, and the level is also important, right? The level of the voltage is also very important. Then synchronization, the transmitter and receiver should be synchronized, and we can use some external clock in order to have that synchronization. We can also use the internal clock. And then of course when we are talking about different encoding schemes, so they should be capable of handling errors. So the performance should be good when there are some errors, because obviously when we transfer data from one point to another point and we have to traverse longer distances, so there are more chances of errors. And when we increase the data rate, so obviously the chances of errors will also be on the higher side. So the performance of those different encoding schemes, it should be good when we talk about the error detection. Also, last but not the least, cost and complexity. So when we talk about some signaling techniques, so we have to manufacture the circuitry, or we have to build the infrastructure in order to have the communication, right? So of course if the complexity is on the higher side, the cost will also be on the higher side. So that is also a key factor when we talk about the encoding schemes. So let's talk about a simple encoding scheme. So here we have represented 0 by some voltage V0, right? Or you can say V0, and then 1 is represented by some other voltage, that is V1. So here we have the data, that is 1 0 0 1 1 1 0 1, and that data has to be encoded, and this is the clock, right? So it means the data is clocked. So this is here we have the duration of the bit, right? And you can see that this is one level of voltage that is representing 1, and this is another level of voltage that is representing 0. So same level, so it means 0, and here we have 1 1 1, and here we have 0 and again 1, right? So the data is 1 0 0 1 1 1 0 1, so this is the same data. So there is some problem. So let's the use case when we have to send 2 bytes, as you know that these are 8 bits, 1 2 3 4 5 6 7 8, and 8 bits is equal to 1 byte, and we have to transfer 2 bytes, and there is a gap between these 2 bytes, and that gap is of 2 seconds. And so in that use case we have to identify the problem with the underlying encoding scheme and what can be the solution. So let's talk about another encoding scheme, that is bipolar, because in the previous case we have a simple encoding scheme, and here we don't have the polarity, we have only levels, but here we have the polarity, and you can see that the 1 is represented by plus 0.85 volt, and a 0 is represented by minus 0.85 volt, and so here we have the polarity, plus voltage and the minus voltage, right? So let's encode this data by using this scheme, and here you can see we also have the clock, so that is the clocked encoding scheme. So 1 is actually from high to low, and 0 is represented by from low to high, and the polarities are different. For 1 we are using plus, and for 0 we are using minus voltage level. So here let's start. First we have to represent 0, right? And you can see that is 0. This is the arrow is upward, right? So I will be mentioning arrow. So this is 0 reference, and here again 0 reference, so this is high to low, so 0, and then high to low, so you can see high to low, and this is 1, so we will be touching 0 again, right, and again you can see that this is 1, right, and then again we will be touching 0, and this is low to high, again 0, and we have to touch the 0, and again 0, 0, so here 1, we have to touch 0, and this is low to high, this is 1, and this is again 0, so 0 1 1 0 0 0 1 0, and you can see that this is the duration of the bit, each bit, so it's the same as a result of this clock, right. So here we are using two polarities, plus and minus. So again we have the problem. The problem is that each time we have to touch the 0 line or reference line, right. So in that case the complexity will be high, and of course the cost will be also on the higher side, right. Okay, so here we have the solution, one alternative of NRZ, two different voltage levels for 0 and 1 bit, voltage constant during bit interval, absence of voltage is 0, right, and okay, so here we have the alternative 1, right. So 1 is, you can see, from high to low, and 0 is from low to high, so this is again plus, and this is minus voltage, right. So here we have to encode the same data but using Manchester encoding scheme, so you can see the transition in the middle of the, right. So this is 0, right, and then we have to represent 1, that is 1, right, and again 1, so 0 1 1, and then again low to high 0, and again low to high 0, and again we have 0, right, and here we have high to low 1 and 0. So this is one alternative, and then we can also have another alternative. So in that case data represented by changes rather than the levels, right, of the voltage. It is more reliable because it's easy to detect the change rather than to maintain the level. So here we have differential Manchester encoding scheme. So you can see that here 0 is represented by the presence of a transition, and 1 is represented by the absence of the transition. So in either case there is a transition in the middle of the bit. So let's encode 100 11101. So this is the clock, and you can see that here we have 1, and then after that we have to perform the transition in the middle of the bit. So this is 0, again transition 0, so here we have 1 because there is no transition, right. So transition is at the beginning, so it is the absence of a transition, so 1, again absence of the transition 1 and 1, so here we have the 0, right, and absence of the transition is 1. So here we have the comparison, wholehearted comparison. So this is unipolar, and you can see data 1 0 1 0 1 1 0 0. You can see we are using only 1, so it means the presence of some voltage is 1. So we can define accordingly or according to our system design. So no voltage, it means 0 1 0. So you can see 1 1 1 voltages, and then polar non-return 0. So you can see we are using polarity plus is for 1 and minus polarity is for 0 1, and then non-inverted non-zero non-return 0 inverted. So this is a sort of differential encoding. So you can see 1 and then 0, no change, no transition, and then on the next one we will be having a change, right? So previous one is voltage plus, so this one will be encoded as negative voltage, and then 0, right? So previous 0 was no transition, and here again you can see that if we are in this negative voltage, so no transition for the 0, and next one will be encoded with the plus voltage, right? So alternate, inverted. So this one is represented by negative voltage. Now we have to perform inversion, so minus and plus, and then again minus, because we are having 3 consecutive ones, so plus minus and plus 0 0, no transition. So here we have the bipolar encoding, right? So you can see we are having bipolar, right, and Manchester encoding, and here we have the differential encoding. If we talk about the differential encoding, data is represented by changes rather than levels. So it's easy for the receiver in order to detect changes rather than to look for the levels, right? So in case of noise, we can also have some sort of sense that there is some transition. So it's more reliable, right, because the detection of transition is easy rather than detection of level. In complex transmission layouts, it is easy to lose sense of polarity, right? So we don't have to look for polarities, right? So here we have some of the pros and cons of different encoding schemes. So when we talk about NRZ, non-return 0, so it introduces our DC component, so it's difficult to preserve that DC component when we talk about the transmission channel, and in that case the transmission channel will be acting as a galvanic path, right? So this can be regarded as one of the disadvantage of the NRZ. So in Manchester encoding scheme, there is no DC component, but there is a clock, so we need more bandwidth in order to use Manchester encoding scheme. So, and the signals can be passed through transformers, AC coupled amplifiers, and other galvanic paths. So this is important if you need the isolation, right? So in that case, AC coupled amplifiers are almost cheaper than DC coupled amplifiers. Okay, and then if we talk about the clock, then the clock has to be generated when we have the scheme which is using clock, and on the receiver side it's not easy task to regenerate the clock, right? So NRZ does not have an embedded clock, so that's why we have to generate the clock at the receiver side, and this is not an easy task, right? And on the other side, if we talk about the Manchester encoding, so the clock is embedded alongside the signaling scheme, right? So it is not a big deal to have the clocked decoding. And in generally differential types offer better noise immunity than the non-differential types. The drawback is that we need differential transmitter and receiver amplifiers, which are more expensive as opposed to the other. So here we have the answer. The signal is decoded by comparing the polarity of the adjacent signal element rather than determining the absolute value of the signal element, right? So level, that is actually the level. So here we have to mention the functions that are being performed by the modem. So we have to convert digital data to analog, and we can also have the scenario when we have to convert the analog data into digital. So modulation and demodulation are analog microwave radio over analog signals, and in that case we have to encode the digital data over digital signals. So this functionality is being performed by the modem, so digital data, and we have to transmit that data or the analog lines, or you can say by using analog signaling. Sequence of data bits and applies modulation to a carrier wave according to the bits is called modulator, a mechanism that accepts a modulated carrier wave and recreate the sequence of data bits. So this is demodulation, a modulator at one end of the transmission medium and a demodulator at the other end. So on one side we will be modulating, and on the other side we will be demodulating. Keep costs low and make the pair of devices easy to install and operate. Manufacturers combine modulation and demodulation mechanism into a single device. So that is why we have modem, modulation and modulator and demodulator. So here we have the modulator, right? Demodulator, M for modulator, D for demodulator. So this is modem that is attached to this computer, and on the other side we also have the modem for wire circuit long distance, for long distances, right? Okay. We can also have modems that can operate radio frequency and optical fibers. There are also dial-up modems, audio tone, and this is a very conventional use case when we talk about that we have the conventional copper pair that is terminating into our premises, and we are using some modem in order to have the dial-up connection. So here we have the scenario that we have telephone office, right? This is the telephone office, and here we have the telephone office, and this is the telephony infrastructure. So the telephone line is terminated at some premises, and this computer is having a modem inside, or it's an internal modem, or there can be an external modem also. So again, on the other side of the network we have another computer, and that is also having the modem, so they can dial each other by using this infrastructure. Then COM applied to dial-up. So the signaling technique that is being used is quadrature amplitude modulation, right? And so we can have different frequency for different data. So data bandwidth is from 600 to 3000, and voice is distributed or between 300 and 3300. So So here we have V32, V32 BIS dial-up modems, and this is the constellations that are being used in case of dial-up modems, QAM for V32 dial-up. Right, so here we have another constellation for V32 dial-up modem. Okay, so the signaling techniques that are being used by the modem, that is amplitude shift keying, frequency shift keying, and phase shift keying. And then when we combine FSK and PSK, we have the QAM. Alright, so these are some of the standards that are being provided by the modems. And then we can also have, this is the QAM, that is the combination of ASK and PSK, 4 QAM, 1 amplitude, 4 phases. So you can see that we have 4 QAM, 1 amplitude. So the amplitude is same, but we have 4 phases. 0, 0 is 1, and then 0, 1, 1, 0, and 1, 1. So here we have 8-bit QAM. So you can see we need 3 bits in order to have 8-bit QAM, 8 QAM, and 2 amplitudes. 1 amplitude is here, so 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 0. And then after that, we have another amplitude, right? So 2 amplitudes, so this is 0, 0, 1, and 0, 1, 1, and 1, 0, 1, and here we are 1, 1, 1. So we can say that 0, 0, 0, and then phase is the same, but we have different amplitude for 0, 0, 1, and then we have 0, 1, 0, 1 amplitude, that is on the lower side, and a higher amplitude, right? 0, 1, 1, right? And then we have 1, 0, 0, 1, 0, 1. So this is the, so here we have different standards, baud rate, bit rate, and modulation technique that is going to be used. Right, so for example, for V90, that is one of the modem that is providing the highest bit rate, right? So you can see baud rate is the same, but the bit rate is 56K, and here you can see also the modulation schemes that are being used. So in order to improve the performance, compression and error correction standards are also being used by the modem. So 2 compression standards, and here we have to do error correction mechanisms. So now we have the answer of our review question. The functionality of the modem is to convert digital information to analog and vice versa. So it can perform the functionality, and in the other way, that it is converting analog signal, we can demodulate analog signal in order to have the digital information. So here we have to compare digital and the analog. So the transmission can be analog or digital, right? So analog transmissions, like analog data, it obviously vary continuously, and there are certain examples of analog data, for example broadcast TV and radio. And when we talk about the digital transmission, the data is represented by using scale waves, and we know the start and the end of the wave or the bit, and the this digital transmission is being used by computer networks. And we can also have interconversion. We can convert digital data into analog and the analog data into the digital in order to represent that data. So here we have the transmission, and on the other side we have the data, right? So we can, if we have analog data and we want to use analog transmission, so the examples are radio broadcast, TV, and again PCM, video standards using codecs, and then we have digital data, and if we are using analog transmission line, the example is conventional copper pair, so we can use a modem which is modulating and demodulating the data, right? And then we have digital data and the digital transmission, so standard LAN cable. So there are some advantages of digital transmission. So the errors are on the lower side, and we can achieve higher data rates, and it's more efficient, right? So here are some of the advantages. Do not get corrupted by noise. You are sending a series of numbers that represent the signal of interest, for example audio and video. Less bandwidth, right? Another way to say that you can cram more information, audio and video, into the same space. Digital can be encrypted. Only the intended receiver can decode it, so security, right? So here are the, if we have analog signaling, and we can use that signaling in order to represent analog data as well as digital data. So here we have the digital signaling, and we represent analog data as well as digital data, but the devices are different. So here we have to use codec, and here we have to use digital transceiver. So in case of analog data and analog signal, so we this is voice, and you can say that this is the telephone that is converting that voice and is launching that voice after the processing over to the analog channel. So digital data, analog signaling, and this is modem. Okay. So there are some of the main reasons: cost, capacity utilization, and security, in addition to privacy, are three main advantages of digital over analog. Okay, so here we have another review question. So how are binary values represented in amplitude shift keying, and what are the limitations? So you can see, so we have different types of analog to digital conversions, right? So amplitude shift keying, and then we have frequency shift keying and phase shift keying, right? And when we mix ASK and PSK, we have QAM, that is quadrature amplitude modulation. So here amplitude shift keying, so 0 is encoded by 1, right, level different carrier amplitude, and 1 is represented by another, right? So you can see the change in the amplitude, right? So 1, right, 1, and then 0, change in the amplitude, amplitude shift keying. So there is a shift in the amplitude, right? So here you can see shift in the amplitude, right? So there are some advantages of using ASK susceptible to sudden gain changes, right? So it has the immunity when we have sudden gain, and here we have one of the cone inefficient, right, and represented by different amplitudes of carrier. Usually one amplitude is 0, right, and here we have bit values, and these are the amplitudes. So you can see that 0 0, this is one amplitude, and then we are representing 1 1 by another amplitude, right, A4, and then 0 1 by another amplitude, A2, and then 1 0, another amplitude, that is A3, right? So here we have the table 0 0 A1, 0 1 A2, 1 0, so 0 0 1 1 0 1 1. So this is how we implement. A digital 1 could not affect the signal, whereas a digital 0 would be making it a 0, right? The line encoding will determine the value of the analog waveform to reflect the digital data being carried. So here the bandwidth B of amplitude shift keying is proportional to the signal rate S. D is due to the modulation and filtering lies between, its value is between 0 and 1. So bandwidth is 1 plus D into S, where S is the signal rate. So here we have, right? So phase shift, it's shift in the amplitude, one signal element and one signal element, right? And one signal element, right? So bit rate is 5 and baud rate is also 5, right? Because 5 ones are presented by 5 signal elements. So here we have binary amplitude shift keying, right? And you can see that this is binary 1, binary 0, 1, 1 and 0. So here is the carrier signal. So we have to modulate this, right? So when we will be modulating this with this one, right? So there will be a change in the amplitude. So shift in the amplitude, you can say modulated signal, right? So it's the, here we have the oscillator that is generating the carrier frequency, and here we have the input data, that is the binary signal, and after the multiplication or modulation we will be having this output, right? So here we have the answer of our review question, right? So with amplitude shift keying, binary values are represented by two different amplitudes of carrier frequency. This approach is susceptible to sudden gain changes and is rather inefficient, right? So you can see this is the binary ASK oscillator that is creating the carrier, and here we have the data and we are modulating, and after modulation we have this output. So what is NRZL and what is the major disadvantage of this encoding scheme? So here we have different line encoding schemes or signal encoding schemes: unipolar, polar and bipolar, multi-level and multi-transition. NRZ, that is unipolar, and in polar we have NRZ, and biphase, then Manchester and differential Manchester, and these are polar, bipolar, AMI and pseudo-ternary, and in multi-level we have 2B, 8B, 6T and 4D, PM5, and in multi-transition we have MLT3. So if we talk about the line encoding, so they should be able to detect errors. So errors occur during transmission due to line impairments. So the codecs, some of the codecs, they perform efficiently in the presence of noise. So we will be, of course, choosing the encoding schemes that give better performance in the presence of the noise. Transition is not part of the code. When it occurs, the receiver will know that a symbol error has occurred, right? So noise and interference encoding techniques that make the transmitted signal immune to noise, right? Interference cannot be corrupted. It is stronger than error detection. Complexity, of course. So here we have unipolar, are one side of the time axis, either above or below. Now return to zero scheme is an example of this code. The signal level does not return to zero during the signal transfer, right? So here we have unipolar NRZ, right? So 1, and this is 0, 1, 1, and this is 0, unipolar, Okay, and then polar. So here you can see that we are using two polarities, 0 1 0 0 and 1, right? No inversion, next bit is 0, right? Inversion, next bit is 1. So this is NRZ inversion 0, and then you can see 1 and 0 0, and next one we have to perform the inversion, right? So this means no inversion, and here inversion, right? So you can see that we have filled this with black ink, right? So again inversion and no inversion. So you can see. So here are some of the points that we have to mention where we are talking about non-return to zero level, easiest way to transmit digital signal, right? And voltage remains constant during the bit interval. No transition, absence of voltage is 0, right? And here we have the answer. Non-return to zero level is a data encoding scheme in which a negative voltage is used to represent binary 1 and a positive voltage is used to represent binary 0. And the one of the disadvantage of NRZ is that it is difficult to find out where one bit ends and the next bit begins, because this is important when we talk about the receiver, because receiver has to find out that when the bit is going to start and where it has to end. And then we have to differentiate QPSK and offset QPSK. So quadrature PSK, more efficient if each signal element represents more than one bit, right? So can use 8 phase angles and more than one amplitude, right? So this is the case of modem. So here we have the transmitter, right, for offset QPSK, right? So you can see that binary input, and we have two right, AN plus minus 1, and here we have QT BN plus minus 1, right? So we have serial to converter, and those bits are serially parallelly fetched over here. So here we will be performing modulation, and this is the local carrier that is being generated locally, right? And we are giving a phase shift of pi by 2, and this is cos and this is sine, and here we are performing or adding up the signals and signal out. So in QPSK, signaling the bit transition of the even and the odd bit streams occur at the same time instant. Offset QPSK, signaling the even and the odd bit streams M1T and MQT are offset in their relative alignment by 1 bit period, half symbol period. A delay of 1 bit time in the Q stream, right? So this is the main difference when we talk about. So here we have the QPSK transmitter and QPSK receiver. So now we have to mention what is a QAM. So when we talk about the phase shift keying, so you can see here we have the time axis and amplitude axis. So we have to represent digital data by using phase shift keying. So you can see this is your phase shift, right? And then 1. So again no phase shift, right? So it means no transition of phase, that means 1, and again we have transition of phase, right? So it's 0, right? And then if again transition of phase, so it's 1, right? So each time we have a transition, so we will be representing a different bit, so it's 0. So you can see here we have the transition of the phase, right? So if 1, 1, next time we will be representing 1, so it means there is the same bit, right? So no, so one baud, and the time is 1 second, so you can see the bit rate and the baud rate, they are the same, right? So we can enclose or envelop more bits in this baud if we are using some other mechanism. 0 bit phase 0, right? And 1 bit phase 180 constellation diagram, and here we have 4 PSK. So now we are using or enveloping more bits, right, in one baud, right? So here you can see that 0 1 2 bits, and we are having and 1 0, right? So again phase shift and 1 0, right? No phase change, right? So the same one baud, and here 1 1 0 0, right? So 2 bits are enclosed in one baud, so bit rate is 10 and baud rate is 5, right? So here we have 4 PSK characteristics, and these are 2 bits, 0 0 phase 0, 0 1 90, and then 1 0 180, and 1 1 270. So this is the constellation diagram. So here we have 8 PSK tri-bit. So you can see 0 0 45 0 0 1, then 90 0 1 0 0 1 1, and so on and so forth. So this is the constellation diagram. So here we have the bandwidth for the PSK, right? So again, this is the FC carrier frequency, and FC minus n baud divided by 2 FC plus n baud, right? So this is the upper frequency and this is the lower frequency. Transmission is same as that required for ASK transmission. Max baud rate for ASK and PSK are the same for a given bandwidth. Bit rates could be 2 or more times greater. So here we have QAM. So whenever we combine amplitude shifting and phase shifting, we are having the QAM. X variations in phase and Y variations in amplitude, it will give us X times Y possible variations, right? So 4 QAM and 8 QAM constellations. So you can see we are using phases and amplitudes also, right? So 0 0 0 1 1 0 and 1 1, 4 QAM 1 amplitude, right? 4 phases. So 8 QAM, so 2 amplitude 4 phases, right? So this is 1 amplitude 0 0 0 0 0 1, another amplitude, right? So you can see that we are using 8 possible variations, 4 possible variations, right? So time domain representation for 8 QAM signals. So you can see 1 baud and 3 bits are enveloped in 1 baud. 1 0 1 1 1 1 0 0, so phase change, right? So another signaling, right? So you can see the phase shift and the amplitude shift, right? So phase, right? Phase and amplitude also. 3 bit, right? 0 0 1, and again here we have right? So here we have the phase shift, right? And the amplitude is the same, right? And 3 bits are actually enveloped in each baud, right? So here we have 16 QAM constellation. We can use different configurations, 3 amplitudes, 12 phases, so 4 amplitudes and 8 phases, and 2 amplitudes, 8 phases, right? So different configurations for 16 QAM, right? On asymmetric digital subscriber line, ASDL, and it's a combination of ASK and PSK, logical extension of QPSK. Send 2 different signals simultaneously on same carrier frequency. So here we have the answer. advantage of the fact that it is possible to send two different signals simultaneously on the same carrier frequency by using two copies of the carrier frequency, one shifted by 90 with respect to the other. Each carrier is ASK modulated, right? So that's all for today's lecture. So today we talked about differential encoding. We have also discussed different functionalities performed by modem, that is the device actually performing modulation and demodulation in order to launch the data or analog line and then receive the data from the analog lines in order to convert it into digital data. Then we also talked about advantages that are being provided by the digital over the analog, then certain limitations that are being offered by binary amplitude shift keying, and we have also talked about the disadvantages of NRZ-L, and after that we compared QPSK and offset QPSK, and finally we have discussed QAM in details, and we have different constellation and different QAMs for 4 QAM, 8 QAM and 16 QAM, and then we have also talked about different configurations, different constellations that are being used in order to have QAM. So that's all. आज के लिए इतना ही काफ़ी है. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफ़िज़. अस्सलाम वालेकुम. So let's have complementary session for signal encoding and antennas. So before starting or before taking some questions, so let's talk about some concepts, that is multiple FSK, frequency shift keying. So here we have the mathematical representation for MFSK, and you can see the formula. This is the signal, A is the amplitude, and this is cosinusoid, and over here we have Fi, that is equal to Fc, carrier frequency, and Fd is also involved over here, that is the difference frequency, and M is the number of different signal elements, and L is the number of bits per signal element. So here we have the question with carrier frequency that is equal to 250 kilohertz and the different frequency of 25 kilohertz, and M is equal to 8. So that means we are going to use 3 bits in order to represent those different 8 levels. So so let me write down that how we can accommodate 8 levels. So if I have to start from 0, 0, 0, so that is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, and 1, 1, 1. So you can see that we have 8 different levels starting from 1, 2, 3, 4, 5, 6, 7, and 8. And we are going to assign the frequencies those different levels. So F1 is assigned to 0, 0, 0. F2 is assigned to 0, 0, 1. So you can see that for 0, 0, 0 we have 75 kilohertz, that is F1, and then for F2 we have 0, 0, 1, and the frequency assigned is 125, and F3 175, and the code is 010, and so on and so forth. So you can see that we have a difference of 50 kilohertz. So if we are going to calculate the data rate, so we can use 1 over T, and we can put the values, and the data rate comes out to be 150 kilobit per second. So here we have another question. Sine wave is to be used for different encoding signaling schemes. First we are using PSK, phase shift keying, and in the second scenario we are using quadrature phase shift keying. The duration of a signal element is 10 raised to the power minus 5 seconds. If the received signal is 0, the following signal has to be received. St is equal to 0.005 sine 2 pi 10 raised to the power 6 t plus theta. So measured noise power at the receiver is 2.5 into 10 raised to the power minus 8, we have to find out the energy per bit over noise N naught in dBs. So here is the solution, TS signal element period, and this is dB is the bit period, and amplitude is 0.005, and we have TS is equal to dB, that is 10 raised to the power minus 5 second. So we are going to calculate the power by taking the area under the curve. So 1 over T, we are integrating, so S square, that is a signal, and we will be, the limits of the integration are 0 to TS, and we will get A square over 2, and if we have to mention EB, energy per bit, P into TB, right? So we are going to place the values over here, and N naught is equal to 2.5 into 10 raised to the power minus 8. So just putting the values in the equation, EB over N naught, we will be getting this equal to 500. Now we have to convert this into dBs, right? Decibels. So 10 log 500, that comes out 25 dB. For B, in the second case, when we are using quadrature phase shift keying, TB, TS over 2, and EB is, as a result, is equal to P into TS over 2, and we have N naught 2.5 10 raised to the power minus 8 into TS. So EB over N naught is equal to 250, and we are going to have the answer 24 dB. Right. So here we have another question that we have to find what signal to noise ratio is required in order to achieve a bandwidth efficiency of 1.0 for amplitude shift keying, frequency shift keying, phase shift keying, and quadrature phase shift keying. So, but we have to assume that the required bit error rate is 10 raised to the power minus 6. So the errors are always there, so that's why we have to take into account those errors. But you know that we have to use the formula EB over N naught, but the figure which we are going to use is not here. So anyhow, we are going to skip this, but you can see that for FSK and ASK, 30.5 dB, PSK 10.5 dB, and for PSK, QPSK 30.5 dB. So you can, from values, you can calculate the SNR ratio for different modulation schemes. So here is another question from encoding. So this is non-return zero level. So this is the encoding scheme when we are actually dealing with the digital data, and we are going to launch, going to use digital signaling in order to launch that data onto the channel. Is passed through a filter with R, that is the ratio, and this ratio is between the bit and the baud. So number of bits divided by the baud. So bit rate and baud rate ratio, and then after that the modulation is done onto a carrier. The data rate over here is 2400 bit per second. So we have to evaluate the bandwidth for amplitude shift keying and frequency shift keying. So for FSK, we have to assume that the two frequencies used are 50 kilohertz and 55 kilohertz because we need that. So for ASK, amplitude shift keying, we have the formula BT 1 plus R into capital R, where capital R is the rate, data rate, and small r is the ratio between the data rate and the baud rate. So after replacing the values, we find out that the ASK, for ASK, the answer comes out to be, the bandwidth comes out to be 3600, and for FSK we are using another formula, that is BT is equal to 2 delta F plus 1 plus R into capital R. So here you can see after replacing the values, we got the bandwidth equal to 8600 kilohertz. So another question from bandwidth, that a telephone line channel is equalized to allow bandpass data transmission over a frequency range of 600 to 3000 Hertz. The available bandwidth is 2400 Hertz, and for a ratio between bit rate and baud rate, that is 1 unit. So it means the same number of bits are being transmitted by using the same number of signals. We have to evaluate the required bandwidth for 2400 bits per second, QPSK, and 4800 BPS, 8-level multi-level signaling. So we have also mentioned that is it enough bandwidth. So let's have the solution. For multi-level signaling, we are using the formula 1 plus R divided by log 2L and then into R. So putting the values, we got out that the L is equal to 2. So now we are going to place the values and we find out that it is 2400 Hertz, and that is just fine for the available bandwidth. And if we are using 8 levels, 4800 bit per second signaling, so here L is equal to 3. So replacing the values, we got 3200 Hertz, and again over here that is not suitable and that exceeds the available bandwidth. So let's have a question from antenna theory. So we have a microwave transmitter and it has an output of 0.1 watt at 2 gigahertz. We have to assume that the transmitter is used in a microwave communication system where the transmitting and receiving antennas are parabolas, and each 1.2 meter in diameter. So what is the gain of each antenna in decibel? And while taking into account antenna gain, what is the effective radiated power of the transmitted signal? If the receiving antenna is 24 kilometer apart from the transmitting antenna, then we have to find the available signal power out of the receiving antenna in dBs. So here we can just use the tables which we have available during one of our last lecture, or maybe you can use the book. So here G, that is the antenna gain, is equal to 7A over lambda square. So as we are given frequencies, so we will be replacing lambda with F square over C square, and after replacing the values, we got antenna gain in dBs 25.46 dB. And for B, we have to take into account that antenna gain. Effective radiated power has to be calculated over here. So that is equal to 35.185 watt. And for C, if we know the distance between the antennas, so we have to find out the loss, right? So this is the loss, and you can see we have the loss 75.14 dB, and the transmitting power in dB is 20. Available received signal power is minus 55.14 dB. Okay, so here we have another review question. That is, we have to find out the height of an antenna for a TV station that must be able to reach customers up to 80 kilometer away. The customers are 80 kilometer away, so we have to find the height. So how high we should mount the antenna so that the transmission can be broadcasted 80 kilometers away. So this is actually the line of sight communication. We can use D is equal to 3.57 kH, and after replacing the values we get H is equal to 375 meters. So mean we have to mount the antenna, that is the transmitting antenna, at this much height. So that's all for this complimentary session. मेरी तरफ से अल्लाह हाफिज़.